committee, I welcome you all and thank you for being here today. Dr. Torres, our director, apologizes for not being here, but he will come to officially inaugurate this workshop after our plenary talk. The annual LEMA Workshop intends to show the progress of the most relevant projects carried out during the year, and to look for new projects and areas of opportunity for joint projects. This year we have the chance to have among us several personalities of the AMS and nuclear physics world. Today we will hear the experiences of Dr. Jules with a long career in AMS and radiocarbon dating at the University of Arizona and in many places where he has been. Dr. Gita Macario is will tell us about the projects with radiocarbon developed in her laboratory in Brazil. Dr. Martin Blau from Belfast in Ireland will tell us about how to analyze radiocarbon data and why base is better. Dr. Padilla from CNA in Sevilla has been helping us to set up the measurements of beryllium-10 and aluminum-26, and he will tell us about his progress on this matter. Dr. Miguel Ángel Carrillo, Elba Ortiz, and Yvette Hill, and Antonieta Mondragon will tell us about the radiocarbon applications in archaeology, environment, and forensic science. Dr. Ciprian Ardelean will tell us about his point of view as an archaeologist about controversial topics regarding radiocarbon dating. This year, the workshop includes talks in nuclear physics, since we have a brand new line coupled to the accelerator. Hopefully, this new line will open many research opportunities, and maybe next year we will be hearing about projects conceived in this workshop. Then I will pass the microphone to Dr. Tim Jules for our plenary talk. Thank you.
Thank you, Corina. So please, Tim.
Thank you very much for the invitation and also for the opportunity to give this plenary talk. Most of the time we have two microphones here, so I don't know if it's good. I should turn one off, I think. Yeah, it's okay. This is, no, it's okay. So in Tucson, we are very close to Mexico because, this is not so good. I will step back. I'll talk over here. Since Tucson is almost in Mexico, it's a nice opportunity to come to Mexico City and explain some experiences that we had in Arizona. And so I had the kind of difficult time trying to narrow down some topics for this workshop, but I'll start out by going through some basics of radiocarbon, since maybe there are some people here who are not familiar with that, and then give you some examples of what we've been trying to do recently, and if I have time, I'll talk a little bit about some other nuclides. So, everybody in the radiocarbon business has a picture. Usually looks like this. So they have different animals here. The Swiss people have cows. I don't know in the Mexican one what's there, but in Arizona we have a mammoth. So we produce C14 in the upper atmosphere by secondary nuclear reactions, that is secondary neutrons produced from cosmic radiation, which then interact with nitrogen to make carbon-14, and we presumably all know that the half-life of carbon-14 is about 5,700 years, and C14 is rapidly mixed into the carbon cycle in the atmosphere and then into the biosphere and other parts of the carbon cycle over a short period of time. And in fact, the time scale of these processes is a very important thing to understand in radiocarbon dating. We can produce carbon-14 in the atmosphere. We can also produce carbon-14 directly in rocks by cosmic rays which interact with rocks. I don't have time to discuss that in this talk. And we can also produce other radionuclides, some in the atmosphere and also in the surfaces of rocks. So those other nuclides can also be used for different kinds of dating. And as we already said, the carbon-14 in the atmosphere is rapidly incorporated into the biosphere. So this is a saguaro cactus over a timescale of about a year. So obviously, this is a very important tracer as well as a dating method. So I'll try and talk about both of those things. We also know that in recent times, since about 1950, we have another source of carbon-14, which is the atmospheric testing of nuclear weapons, which stopped in 1963 or so, except for some small tests. So this is a small test that was done in Nevada. This is called the Frenchman Flat. It's only about 30, 40 miles from Las Vegas, so you can imagine that it must have been very impressive to be in Las Vegas when this thing exploded. And the atmospheric testing added about a factor of 2 of carbon-14 to the atmosphere, which is now almost all re-equilibrated with the ocean, to the point that within a year or so, the atmosphere will become less than the ocean in some places. So this changes the way we think about carbon-14 a little bit. And we also know from the bomb testing that the atmospheric distribution of carbon-14 is not immediately uniform. It takes some time to mix, and the bomb spike produces different zones which you can define by how rapidly the signal is incorporated into the atmosphere in that area. The northern hemisphere is relatively rapidly mixed. The southern hemisphere takes some more time, and also the southern hemisphere has the different characteristic that, as you can see in this map, the southern hemisphere is mostly ocean, whereas the northern hemisphere is mostly continent. So the ocean mixing with the atmosphere is much more important in the southern hemisphere, and this produces a small offset in C14 ages measured in the southern hemisphere. So we'll come back to these ideas a bit later. This is just another plot of the bomb curve showing you that there is in fact some structure on the way up, but on the way down. Now 2018 is the atmosphere and the ocean are almost the same, within 1 or 2% of each other, and as I said, I think by 2021, the ocean will in fact become a source of carbon-14. Of course, the other problem with this interpretation that this is just mixing is that we've been adding dead carbon to the atmosphere all the time. Every year, the CO2 in the atmosphere is increasing by 1 or 2 parts per million, and has now reached about 400 parts per million when it was only 300 and something in 1960. So this is an increase of 25-30% in 50 years. So it's a very large effect, and of course this has other effects well beyond the scope of this talk concerning climate change, for example, which would be a whole other topic. So let's go back to the beginning, and I do have another talk on Thursday, I think, which will talk more about the history of radiocarbon dating. But I wanted to go back to the beginning because the beginning still tells us things that we learn today. So in the beginning, Bill Libby and his colleagues, these are his 2 colleagues, Arnold and Anderson, measured carbon-14 in modern and dead gas samples. The gas samples were taken from the Baltimore sewer and some coal gas, and then they acquired a number of samples from museums that they thought they knew the age of. And this is a plot in the first paper published in Science in 1949, and it's followed up in 1950. And at that time, you could just make a few radiocarbon dates and publish a paper in Science. You can't do that anymore, but so they devised this calibration curve, if you like. This was the first calibration curve that was done. And intriguingly, you can also already see that there are some deviations of the known age from the measured age, which will come back to us later as a problem. And recently, we reinvestigated some of these samples since we knew where most of them were, and we actually found a couple of small mistakes, but in fact, this plot is really a very good plot. And considering the conditions, so this is the graduate student and the postdoc. Okay, the Nobel Prize winner is not in the picture. He's not doing the measurements. They are sitting in the heating tunnel underneath a building in the University of Chicago, and they have a oscilloscope and a screen wall counter that's a solid graphite counter, and a lot of batteries. These are all the batteries to run this equipment. So if you can imagine using this kind of equipment today when we all have accelerators and much more complicated machines, you can imagine that this was a very difficult experiment, not to mention the fact that it's obviously very hot down here in this heating tunnel. So nowadays, we have lots of accelerators. I think there are now about 130 AMS labs all over the world. This is a picture of the Arizona 3 million volt Pelotron. And of course, over time, measurements of C14 have gradually gone to smaller and smaller machines. So now we have machines like this one in Debrecen, where I'm working some of the time. This is a Mikadas. It's about the size of a stable isotope mass spectrometer. It would fit easily on this space here, and maybe 1-2 meters each way. And so this is basically the state of the art at this time. Some people talk about going to smaller techniques, smaller equipment. This may happen, but now I think there are at least 20 of these machines either on order or already installed in AMS labs, and we have a total of, I think, 130 AMS labs around the world. So the basics, probably everybody knows that, but I'll mention it briefly. We produce negative ions usually from graphite, but also from gas. There are now several ways to produce C- from gas. In a sputter ion source, we accelerate the ions. We pass them through an accelerator, which can be anywhere between 200 kilovolts and several megavolts. We strip the negative ions to positive ions, and then we do mass spectrometry to isolate the C14 from everything else that might possibly be there. And obviously, depending on the exact configuration of your machine, how you do that might vary slightly. But these are all basic electrostatic and magnetic elements that are familiar to anybody working in an accelerator lab. And the signal is very clean. This is the C14 signal actually of a blank at Arizona, and you can see there's just some noise here, which may be some C13 or maybe some other ions that got into the detector, but the window separates them from the C14 peak. So the experience is that C14 can be totally separated from everything else in almost all AMS machines. So how do we do the chemistry? A very important part of carbon-14 is the chemistry, because although this list says sample pretreatment, target fabrication, and pressing the sample into the target holder, the first one is the real problem. The second one and the third one are just operational things. And so there are many, many different ways to do the chemistry depending on the sample. I won't explain all of these, but the carbon-14 can be measured on at least the kinds of samples listed on this list, and probably many more. So we can extract carbon-14 from wood samples, from shells, from groundwater, from carbonates, even from iron slag, so iron that's been fired with charcoal, not with coal, and also even with meteorites, which we've done at Arizona. And also bones, which have various ways to extract the organic material, the collagen, from the bone for dating. And so that is also a whole other talk, but it's just to say there's a lot of different chemistry that needs to be done before you get to the AMS measurement part. So we can skip this picture because it's just a nice picture to remind you that we're dealing with the carbon cycle. And as long as our sample is in equilibrium with the atmosphere, so this is the case for most of the terrestrial biosphere. In the case of the plants or animals living in the ocean, they're in equilibrium with the oceanic reservoir, which has a slightly different C14 to 12 ratio than the atmosphere, and therefore produces slightly different ages, which you have to correct for in your calibration process. So this is a model of the whole biosphere, which, as you can see, is rather complicated. And if you have samples that are in equilibrium with the production process, everything is fine. If the production process is disturbed in some way, then your signal will diverge from what you expect, and then that's where it becomes interesting, actually, because this is telling you some physics or chemistry. So we'll come back to that idea in a few slides. So I'm often asked how C14 ages are defined, and they're defined in some rather strange way as relative to 1950 AD, which is not actually correct because 1950 doesn't have the value defined as modern by Stiver and Pollack. It's actually about 2% lower, because by 1950 we already have addition of dead carbon to the atmosphere from industrial activities. But in any case, there's some value which is taken as 0, and we can then, if we know the amount of carbon-14, we can calculate the radiocarbon age, that is just assuming radioactive decay. And then, as we all probably know, the production rate of C14 in the atmosphere varies with time, so we have to adjust for the fact that there's another variability which occurs, which I will also come back to. And there's some other normalization questions, but they are not very important right now. There are some standards which were made by originally the National Bureau of Standards, now National Institute of Science and Standards and Technology, and there are also many secondary standards, IAEA and other sources, which are available. So once you have a machine, you've done the chemistry, you can make the measurements, then you need some kind of a standard, and then you can move on. And so it's also important, I just threw this slide in, to remember that you also need to know how accurate your measurements are. You need to define your measurement against known standards and also known blanks. And the blank should be obviously a blank of your whole process, not just some graphite stuck into the AMS target holder, which doesn't reflect the chemistry. So how well can we do this? This is a measurement which is done some time ago where 3 different labs took the same olive pits. So they had olive pits from an archaeological site in Israel, and they divided up the olive pits into several pieces, and they sent them to the different labs. And so this is the result. You can see that the standard deviation might be something like 10, 20 years. This is kind of typical of relatively good, now some people claim better precisions, but this is actually reproducibility as well. So you can see that reproducibility of different labs is of the order of plus minus 20 years in the radiocarbon age. You then have to remember that we have to calibrate this using the calibration curve, so there's another source of error to add in. So the weighted average of all these dates is about plus minus 10 years, which I think is about as well as you can do almost anywhere. And in fact, once you start calibrating the result, the calibration curve has an intrinsic error of at least that. And this is often forgotten by people doing calibrations. So the calibration is very important. This is an old plot of the calibration curve. I just happen to like this picture. the newer calibration curve is revised every few years. There's a new revision of the calibration curve going on at the moment. And so whenever you do a calibration, you have to report which calibration curve you used, or which software you used, because obviously there might be some small differences in the results. How was the calibration established? We used known age material from tree rings, and it was then extended using other proxy methods, particularly uranium series dating of marine samples. And so the tree ring record goes back to about 12,500 years, and it's based mostly on European oak trees and also some other trees such as this, which is a bristlecone pine, which is growing in White Mountains of California at rather high altitude, over 3,000 meters. So these trees are very close to the tree line. And at this altitude, 3,300 meters or so, forest fires don't happen. So the dead wood remains on the ground, and so you can then find dead pieces of tree and living pieces of tree and make a long time series. This tree is one of the oldest trees, which is about over 4,500 years old. There was an older tree, which was about 5,600 years old in this site, which was cut down in the 1950s by a graduate student. I guess he did actually finish his degree, but anyway, there's a lot of old wood in this area. The European chronology is mostly based on wood found in bogs in the Rhine Valley and in Ireland. And you may, I think, hear about this from another speaker later. So one of the main approaches is to use C14 for dating. We've dated all kinds of interesting objects, ranging from religious objects to historical and archaeological objects. And obviously there's a lot of archaeology and geology that's done with C14 dating. I only show a few examples here. This is a Dead Sea Scroll, which is actually the book of Isaiah, and this is dating from about 150 BC. This is a fresco from the 10th century in Europe, and this is a silk from India, maybe 16th, 17th century, and this is a bust of Nefertiti, which is in the Neues Museum in Berlin. It used to be in a different museum, and so the Neues Museum is actually very old. That's just the name of the museum, and so this is about 3,000 years old. And so obviously most radiocarbon labs have all kinds of stories about famous artifacts that they've dated from the Shroud of Turin to the Easter Island statues. So I showed a few pictures here highlighting those things. And obviously when you make your presentation to the public, you like to highlight those kinds of things. However, we can also do other studies of C14 and also try and understand the processes that affect C14 and maybe also some physics. So in Arizona, we have a very large tree ring lab, which is basically across the street from the AMS lab, which is very useful because this means we have access to a very large catalog of many old trees, most of which are documented, some are not. I think there are like 1 million pieces of wood in this catalog in Arizona. And there are one or two other places in the world, I think in Belfast and Zurich, where you have some similar collection of wood. So this is one example. This is a sample of sequoia dating from about 800 BC. So this has been dated by dendrochronology, so it's absolutely dated by cross-referencing different trees. And obviously you can see that the width of the rings fluctuates with time. You can see something that looks like maybe an 11-year cycle, which is a solar cycle, and you can also see other structure, perhaps reflecting changes in climate or changes in the conditions that the tree experienced. So sequoia is actually easier to do than bristlecone because the tree rings are much wider, but I just show this as an example. So we have many ways to calibrate carbon-14. We have the standard calibration curve, and then there are several different software packages which are basically freely available. And using that, you can calibrate your age. And then, of course, the next question is, what does that mean? The calibration curve is not a straight line. It's not even a curve. It has a lot of structure. And this structure tells us something about what's happening to the C14 in this carbon cycle at that time. And so this blue line also conveys information. If you're just using this for dating, then you have a raw radiocarbon age, and you can calculate a calibrated age. You can see that sometimes there are multiple intercepts, which you then have to evaluate as to their significance. And depending on the exact time point where your result falls, you will get more or less precision in the calibrated age. So this one is a very precise one, and this one is a much less precise one. And you can see this is a different time than this one, which is about 1,000 years different. You can also use sequences of dates. So if you have dates that have some known chronology, either in tree rings with known age differences between them, or maybe a sediment core where you have some idea about the relative, the superposition of the samples, for example, you can also maybe better constrain the results by using some sort of sequencing, which is also available in certainly in Oxcal and some other calibration packages. And so this is one example of this is actually a tree from Hungary, I think, and we actually had a number of samples with known gaps of 9 years between each sample, so they were every 10 years. And instead of what you would get with one measurement, which would be the gray bars, you can get a more refined age by combining a number of ages which are in a known sequence. So the next question is, what can we learn about this variation of C14 with time? Because this variation in the calibration curve is telling us that the carbon-14 production in the atmosphere, or the cycling of carbon-14 in the atmosphere, is not constant. And this is telling us some physics about carbon-14. So in the past few years, we spent a lot of time looking at large excursions in carbon-14. The most famous one occurs at 774 AD, which you can look up on Wikipedia, so I don't have to explain it. At that time, there was a large shift in carbon-14 between 1 year and the next of something like 100 years in apparent age. So obviously, if you dated a sample from 775 as opposed to 773, the apparent age difference would be 100 years, even though they're only 2 years apart. So this tells us that we don't know enough about the calibration, and we need to perhaps go to more annual data as opposed to decadal data or bidecadal data, which is what is used to make up most of the calibration curve. So this lady, Fusa Miyake, was one of the people who started these studies in 2012, and she recognized a large event at 774 AD. And so this is a picture of her actually when she was in Arizona. And it's useful because maybe some people don't know this terminology to define this term, which is called delta C14, which is the C14 value corrected for its true age. And if we correct C14 for its true age, then we have a parameter that tells us the deviation of the production rate then to the production rate today. And so we express this in parts per mil. This gives us some idea about the relative change in C14. So what can we see? Let's skip these. We know that the C14 production rate can vary, and therefore we then have to wonder what causes these changes. And so, assuming everything else is the same, if we have a very rapid change, the only thing that can really change is the production of the carbon-14, which is from the primary cosmic radiation. So therefore, we have to assume that the cosmic radiation changed with time. And then we have to ask what can cause that. So we have several possibilities. There are a few others, but these are the ones that are often discussed. The main one, which is used to attribute to the 774 event, is a large solar proton event, or a coronal mass ejection event. And in fact, this has dominated a lot of studies of annual data for the past few years. So some people are also interested in supernova, which I'll come back to at the end of the talk. And this is a study by D et al. Published last year, 2017, where they looked at several proposed supernova. Most of these are real, this one is not. These were observed supernova in astronomical records. And so the question was whether or not you can see a change in C14 as a result of a supernova. Now, obviously, these supernovae were some considerable distance from the Earth. The 1054, I think, is 5,000 parsecs, something like that. So a long way away. And obviously, if the supernova was too close, nobody will be here to measure the data. So obviously, there's something in between the two extremes is possible. Here, you don't really see any change in C14, except maybe in this 1054, which is a Crab Nebula supernova. And so this is a whole other interesting question as to whether supernova can produce carbon-14. And in fact, this is not a new idea. This was thought about 20 or 30 years ago. It's just that at that time, people didn't have the resolution and the precision of the AMS technology to do those types of measurements. So the 774 event, 770, this says 775, I think now it's more or less agreed to be the year before, changed the C14 by about 12 per mil, which is 100 years in the radiocarbon age, in 1 to 2 years. And you cannot do this by messing with the ocean or the other reservoirs of carbon on the surface of the Earth. Those processes take much more time. A second event was found about 993, which is also published by Miyake and also confirmed by a couple of other papers. This event was smaller than 774. And in fact, a few weeks ago, I was at a workshop in Japan where they were discussing these events, and I think that they agreed that this is the largest event in the last 10,000 years, although we haven't studied the entire record in enough detail to say that for sure. But if you look at the calibration curve, which is based on 10-year intervals of tree rings, there is nothing that stands out as being larger than this, since presumably a larger event would be observed in the calibration curve. So this is a summary of Miyake's data from 2012. You can see this rapid change. And obviously, if you're the archaeologist measuring a sample here as opposed to here, you would, using the existing software, get the wrong age, since the calibration curve only shows a small effect at this point. Since then, there have been a massive study of this particular phenomenon. This is a paper that just came out in Nature Communications by Brentgen and I think 50 other authors, where they summarized the data from all these sites. These are all trees which have been measured for this 774 event. And the most remarkable thing is also that this is confirmed from ice core data of beryllium-10 independently. So independently, beryllium-10 and chlorine-36, other cosmogenic nuclides, have been measured in ice cores, which confirm the age of this event. This is a summary of these two events in this paper. Actually, this is a paper by Dee, but anyway, the most remarkable thing is that the amplitude of this event is the same all over the world. So it doesn't matter if you're up here or down here, the amplitude is almost the same. In this paper, these authors, I'm one of the co-authors, so I have to say that, there is some indication that there might be a latitudinal gradient, that is that the production rate is slightly higher in the polar regions, because that's where you would expect more cosmic rays to come down. But the general philosophy in C14 is that the carbon-14 is rapidly mixed in the atmosphere. So this is a confirming paper by McAlvey et al. That shows that this spike also occurs in beryllium-10 and chlorine-36 in ice cores. And so this has to be a very intense change in the cosmic ray flux to produce beryllium-10 in particular, which has a very high Q value. So you don't just produce beryllium-10 from low-energy solar protons. You need at least 30 MeV just to produce beryllium-10. And so that's what we know about this event. So we know that we can have intense solar flares which produce lots of radiation on the Earth, and they also disrupt the geomagnetic field of the Earth. And that's another way that we might change the C14 production rate. This is just a NASA video. So there's one event that we know about, which is called the Carrington event, which occurred in 1859. This is a known perturbation of the geomagnetic record. There was a large change in the geomagnetic field that occurred in like minutes. I think it changed by at least 10%. And there were large aurora observed all the way. I think aurora were observed in Havana. So clearly there was a massive dose of something that hit the Earth and also perturbed the geomagnetic field. However, if you look at the C14 record from this time, which is coming from Stiver in 1998, there's also another paper recently, which I think is unpublished, where these authors confirm this observation. You don't see any change in C14 in this event. And this is a known event that was recorded. There are papers about this massive geomagnetic event. So this is an estimate of the flux of protons. Something like this would have to be maybe a few times higher to produce a 774 event, and something 10 times higher would really have serious consequences. So if you can imagine not just worrying about carbon-14, but if some event like this occurred today, that would be disastrous for the modern technology. Your phone wouldn't work, internet would be down, all kinds of other things would happen. There are reports at this time of aurora around telegraph wires. So at that time, in 1859, text messaging was done by telegraph, but the telegraph system was disrupted. So you could imagine today this would have much more consequences. So we want to look for other records of these phenomena. And then we also want to think about how can we use this to our advantage. So there are many records, particularly in the Asian chronologies from Korea and China, not so much Japan, in the last 2,000 years, because the Chinese emperor was very interested in astronomical phenomena, and they would demand records of anything strange that happened in the sky, not necessarily for scientific reasons, but also for other astrological reasons or things like that. So this is very well documented, and so we start looking for other kinds of events. So this is an event which is not recorded, which is much earlier, This is published in 2017. So we went to the calibration curve and looked for places where we see relatively large excursions in the calibration curve, and then if you can extrapolate from that, that if you do this on an annual basis instead of 10 years, you should see much bigger events. So this one, I think, is about 20 per mil, which would be 160, 180 years in C14. And so again, that will be a large change in your actual age. Also, these measurements were done in 3 different labs. So one of the problems with doing these kind of measurements is you have to reproduce them in a different lab, because you're looking at small effects, and you want to make sure that your lab doesn't have some strange systematic error that's not reproduced somewhere else, and also that you can, if possible, reproduce these measurements on different trees. So not just one tree, but one or more trees. This shows the effect on the so the blue line is the calibration curve, and these are the annual data, and you can see that the calibration isn't a very good fit to these annual data, because it was based on different records, and so this has created a whole need to reevaluate the whole calibration curve, which is starting and which will no doubt go on for a number of years. So this event is probably not the same kind of event as the 774 event, but maybe some similar type of process, maybe a solar minimum, so if we have a solar minimum, which occurs every couple of 100 years, the solar magnetic field is reduced, and this means that the galactic cosmic ray flux increases. That's the opposite from having more solar protons, which would also produce more carbon-14. So it's kind of counterintuitive, but it's a different way to make more carbon-14. This is another event measured by Park et al., which is published recently, where they found another one of these strange excursions about 660 BC. This has some interest, particularly in Eurasian archaeology, since it's about the time of movements of people in Asia. So these phenomena are real, and they clearly affect how we understand radiocarbon dating, not just for operational reasons, but also for understanding the processes. So I'll show you 1 or 2 more. This is not a very exciting one, but it shows a similar effect where the blue line, the blue points, the annual data differ from the currently agreed calibration curve. So what are other things that could produce these kind of changes? We know that the geomagnetic field varies, and you can have local variations of the geomagnetic field. This is some examples derived from pottery in the Middle East, but these may just be local phenomena and may not be expressed on a global scale. So there may be other ways to explain these spikes, but so we still don't really understand them completely. But the question is, how can you use this for archaeology? So this is an important question. There's a study by Vaca in 2014. So let's say that you have a piece of wood that has this spike in the wood. In this case, this Swiss group, had a log from this church, which I guess was an original log, and they found that they could obviously sequence the tree rings, and the C14 spike, that is the 774 spike, is in the tree. So this means if you have the spike in the tree and you count the number of rings to the outside of the tree, you know precisely within 1 year the age of the tree. So in this case, these authors were able to do this, and so then they have a precise age to plus or minus 1 year, or maybe plus or minus 0 years, because they have an exact marker in the tree ring record. So obviously this is not going to happen frequently, but if you're lucky enough to have wood that overlaps one of these large events, then you could use this to your advantage to date the object more precisely. Just show you one more example of actually using radiocarbon dating to understand chronology. This is a paper by Ramsey, that is the Oxford group, published in 2010, where they took wood from all the tombs of all the Egyptian pharaohs. And of course, the archaeologists will say that they know the ages of all these pharaohs precisely because it's written somewhere exactly that this pharaoh reigned for 10 years and his follower, his successor, reigned for so many years. There are one or two errors in this chronology, but in general it's very precise, and they find that in the Middle and the New Kingdoms of Egypt, so this after about 2000 BC, the radiocarbon ages and the Egyptian chronology agree very well, but before that time there are some discrepancies, so presumably the Old Kingdom chronology has maybe some missing records, but this gives you some idea of how precisely you can do radiocarbon dating, because it really shows that these ages agree with documentary evidence of the age of the material. Another slightly more controversial topic is dating of the eruption of Santorini, which is an island in the Aegean Sea, which erupted about 1600 BC and caused the end of the Minoan civilization in that part of the world, which was, at that time, I would say, one of the most advanced technological civilizations at that time. And so various people have tried to date this event precisely. This paper used an olive branch which was found in a volcanic ash deposit on the island of Santorini. This is a big volcano that erupted at 1600 BC. So this is somewhat older than the archaeological argued age, which is maybe 100 years younger. And so we've been looking at ways to reconcile these records. Recently we've been using bristlecone pine. And so because we know that the C14 record, based on the calibration curve, doesn't appear to be quite right, we basically defined our own calibration curve based on annual data, and we then find that we can shift this C14 age for Santorini a little bit younger, maybe 20, 30 years, not all the way to the archaeologically defined age of maybe 1550, but in the right direction, so we can at least continue to talk to our archaeological colleagues on this subject. So I have a brief, I don't know how much time I have left. 10 minutes. I briefly returned to the supernova question, and I talk about something completely different. So in 1054, the Crab Nebula supernova occurred. This was a very, very large supernova, which was, according to records, brighter than the sun for several weeks and was seen in the sky for several months. It's well documented in Chinese records and maybe also in Native American records. This is Google. This is a problem with translating a Mac to a PC. Anyway, this is a diagram in Chaco Canyon in New Mexico, which is supposed to represent this event. So we were looking for C14 excursions at this time. I showed you a plot earlier from D et al. That suggested there was a change in C14 about this time, so 1054 AD. And so there's some suggestion that there may be an event here. It's not conclusive. There may be some other overlying solar fluctuations, which we know the solar cycle only changes the C14 maybe 1 to 2 per mil. So we think this might be some evidence of this phenomenon, and we're doing more studies. Obviously, this would be the photons affecting the C14 directly. The question then would be, can you see the protons, which would arrive much later because the protons don't go exactly the speed of light. So if we could show that supernova affect C14, that would be something very new and something that other people have looked for in the past. Obviously, this supernova is about 5,700 parsecs from the Earth, so it shouldn't have a very large effect. So I moved to a different topic just to change because I said I would talk about more than one radionuclide. I'd like to highlight briefly some studies we've done on iodine-129, which is a long-lived radionuclide mostly produced by fission. It's also produced by cosmic radiation, so it's also a cosmogenic nuclide, but these days the signal is swamped by anthropogenic sources of iodine, most of which are nuclear, well, all of which are nuclear. So this can be produced by spontaneous fission, by cosmogenic processes, by cosmic rays interacting with xenon in the atmosphere, or by nuclear processes, mostly nuclear testing, but also nuclear reactors. And so the anthropogenic iodine signal has changed dramatically from the pre-bomb value to the current value by orders of magnitude. This is a list produced by this group, Ho et al. So they do a lot of work on iodine-129. They're in Ho is in Denmark, but the measurements are made in China. And there are also many measurements made by several other groups, particularly in Japan, on iodine-129, and also at Arizona. So these are different sources of iodine-129 in the environment. This is the natural source, and this is a much larger source, which is from nuclear fuel reprocessing, of which there are several known facilities, mostly in Europe. There are two. There's one in France and one in England, which produce most of this iodine-129 production. There's a smaller amount which is produced from Hanford, which is in Washington State. And I think there's also a Japanese reprocessing plant which doesn't have much effect on the total. So these are large amounts. They're like 5,000 kilograms of iodine-129. There's a lot of iodine-129. And we have measured iodine-129 in the Columbia River, which is flowing past this Hanford site, which accounts for a significant amount of this iodine-129. So originally, a French group, Yu and Reisbeck, discovered this iodine-129 signal in ocean samples in seaweed, and they found a dramatic increase in the North Atlantic starting in the 1990s, which timed exactly with the scaling up of reprocessing by the French facility at La Hague, and there's also a British facility in Sellafield. So if you measure iodine-129 in the North Sea or the Irish Sea or the Atlantic coast of France, the amount of iodine-129 is very high. You can see these numbers are, I don't know what these units are, but anyway, they're a very large signal. So iodine-129 is actually quite easy to measure. I'm not sure you could do it on a 1 million volt machine if you have a big enough magnet. That would probably be the limiting factor. You can do some chemistry and extract the iodine either with an ion exchange column or by some more simple chemistry where you extract iodine into chloroform and then react it with silver powder, which is quite easy to do. And that's what we do at Arizona. So I had a graduate student and also a postdoc who spent some time trying to expand these studies to other records of iodine-129. This is another process of Ho et al., which involves co-precipitation of iodine with silver chloride, which is another way to do the same thing. Biddulph et al., was at Arizona, studied corals from the South Pacific, and he found that in the Solomon Islands, which is in the western South Pacific, the iodine signal increased much more rapidly over time than in Easter Island, which is in the eastern South Pacific, closer to Chile. And obviously, the time for the iodine signal to circulate into the southern Pacific Ocean, close to South America, will be much longer than in the western Pacific, where it's much closer to the source of the iodine 129. And so Ginger Chang, she was in our lab. She just moved to Florida, decided to look in another record. This is a record of coral from Vietnam. And she found a very rapid change in 1 year, which we initially didn't understand, but we then looked at records of atmospheric nuclear testing, which are now mostly available, and we found that we could attribute this to specific American tests which occurred in the Marshall Islands in the 1950s. This is another, don't worry about this part. This is a diagram done by a Japanese group who was studying the same kind of things, Bautista et al., and this is what they defined as the circulation of iodine 129, the sources being from Europe or from nuclear testing in the Pacific, and they were interested in 2 sites in the South China Sea, which is a whole other topic, and also obviously we measured the Solomon Islands, and this is Easter Island. These are some other sources. There's 2 North American sources, which are Hanford and Savannah River, which are also reprocessing nuclear fuel. So the Japanese colleagues studied these sites, I think the Parola site and this site in the Philippines, and we studied Condau Island and also the Shisha Islands. Okay, these islands have some other name. This is the name that the Chinese give to these islands. So since the Chinese are in the business of taking over most of the sea, but anyway, so these sites showed this significant jump in iodine 129, and this sea is kind of isolated from the Pacific. It's relatively shallow, and the water only dumps from the Pacific into the South China Sea every few years. So the oceanography is a little bit complicated, and so the Japanese group, because they looked at sites on the eastern side of the Philippines, also got some more information. So in this paper, we also looked at samples from Guam, which is in the western Pacific, and here you can see very high values of iodine 129 in corals in the late 1950s. So coral is growing, it grows different layers every year, sort of like tree rings, so we have an annual record. And so this is quite clear that this has to be from nuclear activities, particularly since Guam is relatively close to the Marshall Islands, and so we went down this road. The Japanese group also did some similar studies where they were able to even get very precise information about the timing of these signals. So we know, so all this information about these nuclear testing is now mostly declassified and publicly available. These are nuclear explosions that we know occurred in the Pacific Ocean. So we have obviously the 2 atomic bombs in Japan. We have American testing here and French testing, which occurred here, but the French testing was pretty low level and not very large. Some of these tests in the Western Pacific in the late 1950s were very, very large nuclear explosions, and you can see pictures of them on the internet. And obviously this testing was all banned after the Test Ban Treaty of 1963. So the question is, does this signal get over here? And so Ginger did a lot of modeling. These dates aren't exactly the dates of the event because the software didn't go back far enough, but this shows you that the water can get into the South China Sea every few years, not every year, and so that allowed us to say that this signal is definitively caused by these very large nuclear tests, ones in Bikini and Anahuac, which were conducted 1954 to 1958. So finally, I'll finish up. We also tried to look for a signal from a Japanese nuclear event in 2011, which is the Fukushima nuclear plant accident, which dumped large amounts of radioactivity into the ocean, mostly because they flushed in order to shut down the reactor, they flushed it with ocean water. So these are some signals measured close to the reactor, and this is a IAEA report of this plume of iodine moving away from Japan. So the question is, does this get to North America? And the answer is, it's not completely clear. We've been monitoring iodine in San Diego since 2011, and we don't actually see this signal, although there were reports from northwestern US and Canadian measurement buoys in the ocean that cesium has been measured, but not iodine-129 or even other similar nuclides. So the jury is still out on this particular study. This study now goes to 2018, but you can only see an annual variation of iodine-129, which was we attribute to biochemical processing, exchange between iodide and iodate in the ocean, perhaps. There's one report from a Romanian group that suggests that they measured iodine-129 in San Diego in 2015, but this has not been confirmed independently. So I think I'll stop there and answer any questions.
Thank you. Okay. Well, thank you very much, Tim, for this fantastic talk. And we have time for questions and comments. Corina.
Thank you, Tim, for this wonderful talk. I want to ask you about when you do the analysis of the same sample, for example, in this event, 5,000 years before present, and you collaborate with several labs, and do you agree in using the same procedure to have this wonderful agreement?
Yes, okay, and those samples were all converted to cellulose, but we used the whole...
Is exactly the same procedure?
Almost exactly the same procedure. There may be some local difference. So, some people, when they extract cellulose, also do this final base treatment to go to what they call alpha cellulose, which is a little bit cleaner. But we find that the holocellulose after the bleaching is sufficient. In that case, we measured the samples from 3 different kinds of trees, from bristlecone, from a Japanese cedar, and from European oak. So there's 3 independent measurements. And also, so the procedure varies slightly, but not very much. I guess that's the answer.
Well, thank you. Thank you very much.
Good morning. Not being an expert of the area, I found really fascinating actually your talk. So I have basically 2 questions and will be terribly basic, I believe. The first one that I got very surprised when you were showing the change in CO2 in the atmosphere, and it has a kind of a slow change all the time.
Yes.
I was wondering why is that? I mean, such a fast change in the concentration over the years.
In the winter, there's more CO2 produced by anthropogenic processes, and in the springtime, the trees suck down the
It was
CO2.
very basic. I have another one which is again very basic, but I was
Yeah.
really curious. When you get a tree, for instance, from the church, as you found,
Yeah.
this is a tree wherever it was cut at a certain moment, you don't know where, and you start counting the rings, and you can give a year per ring. I was wondering, how do you manage to get the offset, basically, for the starting point? Probably that would be extremely.
Well, in this case, they had a tree. They didn't know the age of this log, except they knew it was old, and they suspected that you could find the. Okay, usually we have some physics problems. So usually with dendrochronology, you have to have a sequence you can overlap with an existing sequence. In this case, they didn't have that. They just had an isolated log. So then they suspected that it overlapped with the 774 AD, and so they looked at the carbon-14, and they were able to show that this spike occurred in the log, and so then they were able to cross-date it precisely. So it's a little bit more complicated in that case.
Any more questions? Luis?
In the case of the iodine samples, how deep you have to go inside of the ocean to have the sample?
How deep?
Yeah, inside. It's surface, or you have to
These
go
samples are mostly on the surface, yeah, or from corals. So
and close to the coast?
well, because the coral is growing on the coast in more tropical regions. So if you can find the coral, they collect iodine. So 30 degrees north-south, you can find corals growing. So if you have the coral, you can do the measurements.
I will have a question, a more technical kind of question, which is related to the shrinking size of the facilities.
Yeah.
You're talking about these Micadas, which is 250K kilovolt accelerator, and what we struggle here, well, we don't struggle, but this is one of the problems, is the molecular contamination.
Yes.
So how do you handle this in the smaller machines?
So in the smaller machines, they turn up the stripper gas. That's the main way they get rid of the molecules. Basically, you have to run the stripper gas at a higher pressure, and then you also have to check that there are no molecules coming into the detector, and they have a kind of ad hoc way of doing that, which is to cut the beam in two and then see if it's the same on both sides. That's a ad hoc solution. But the Micadas machines don't show any background above the regular blank if you run a blank sample, so that suggests that as long as you run it under the correct conditions, it works fine. If you don't have enough stripper pressure, then you may have problems. I mean, if you're using 1+, this is always a potential problem, right?
Okay. Sorry. Okay. Any more questions, comments for Tim? Okay. Otherwise, let's thank him again for this wonderful talk. And we have a break for coffee, and this is a present from Corina to Tim. Thank you. So we come back here according to the program at 11, I think. Thank you very much. So, did you get a copy of the presentation?
It's on the, you can use it.
Thank you. Thank you very much.